Hello, in this video, I'll go through the implementation of reinforcement learning for drone delivery. I have five research questions: which reinforcement algorithm will perform better, and how do the variance of the parameters affect the results? How do the obstacles also affecting the results and the learning? And whether the reward function also gonna change the behavior of the agents? And can multi-agent reinforcement learning scale for example, two drones and delivering five packages? The environment is a simple drone delivery environment where the drone has to deliver a package to a location. We have some obstacles. As you can see, we have tree, dogs, and birds, and the drone is needs to deliver this package to the location of X. So we have started with the DQN-based reinforcement learning approach. However, instead of using the standard DQN, we implemented the 3DQN, which is the dueling double deep Q network. And this is because the normal DQN often suffer from unstable learning and overestimation of Q values. And the D3QN improved this by using the double DQN, which is reducing the Q value from estimation and separate state evaluation from the action evaluation, basically. This generally leads to more stable and efficient learning. And here we define the network architect. So the architect is based on the dueling DQN design, where the network is separated into two streams, a value stream and the advantage stream. First, we have the shared feature extraction layer. This extracts the important features from the environment state before splitting it into two streams, the value stream and the advantage stream. So in the value stream, here we estimate how good the current state is overall, and in the advantage stream, it estimates how beneficial each action in the state. So combining both stream are combined into the final Q value, and which improves the learning stability and helps the network for a better distinguish between the valuable state and the valuable actions. And next we have the buffer. So this stores the past experience and allow the network to train on randomized batches, reducing the correlation between the samples. So the agents explore using the epsilon gradient exploration. At the start, the actions are mostly random to encourage exploration, and the epsilon gradient decrease over time. So the agents begins exploiting learned behavior. So the double DQN here, we implement the double DQN mechanism. So as you can see, this separates the action selection from the action evaluation, which reduces the approximation of the Q values. We also use the target network to stabilize the train by slowing the update target values instead of just changing them every step. So this all basically based on the Bellman equation, as we have seen during the lecture, which is basically updates the Q value using the current word and plus the estimated future rewards. So, however, overall, this implementation still not that good because our environment is a dynamic, and the Q value estimation remained unstable during long training. So this leads to very bad results. So for example, as you can see in our first experience, we had very bad outputs. So as you can see, the rewards are not stable at all. And this is because the epsilon gradient that I first chose is really very not that low. So there is the exploration just start at the beginning of the states. So what I have done is I have reduced the number of the epsilon to a smaller number, and as you can see, I got a better result for this fixed environment. So here we don't have any obstacle moving. However, so as you can see, the model here performs really good. It finds it's delivered the package to the location. However, our environment is a dynamic environment, and as you can see, the results for adding dynamic obstacles that is moving is still unstable, and this is because the how the DQN is implemented. So as we saw that the DQN performed very poorly on this environment because the learning become unstable and the agent struggles to constantly improve. Therefore, we have implemented the PPO, which is the proximal policy optimization, which is much more stable reinforcement learning algorithm for sequential decision-making tasks like drone navigation. The architect is based on an actor critic model. So the actor decision which action the drone should take, while the critic evaluate how good the current state is. And here we can see the actor network. So the actor outputs the probabilities for each action using the softmax, allowing the agent to explore different actions instead of just choosing the same one. And here the critic network. So the critic estimates the value of the current state. This helps stabilizing learning by guiding the actor. So one of the key parts of the PPO is that compare the old policy with the updated policy. This allows the PPO control how much of the policy changing during the time. And here the clipping mechanism. So this is the one of the core reason why PPO is more stable than they can, because it prevents the large update that could destroy learning. So we use gamma 0.99 to prioritize the long-term rewards. So finally, the agents collect the experience from the environment, store them, and update the actor critic network using the people optimization. So the first experiment that we have done for PBO is no moving obstacles. As you can see, in very short stage, the model stable and gives a really good outputs. So here is an demonstration. As you can see, the agents has successfully delivered the package to the location. So in a cooperation between the PBO and the DQN on the same environment, there's no moving obstacles. As you can see, that the PBO really performs better here. So we have started experiment with more dynamic environments. So now we have two birds that is moving and two dogs. So as you can see, we have still getting really good outputs for approximately 5,000 states. As we increase the number of birds and dogs, it also gives still gives a good results. However, it's decreasing the number of states that it's taking in order to achieve the stable state. So then I have started comparing between these results, as you can see here. Then we have started changing the parameters in order to see how these parameters influencing the training. So the first parameter that we have changed is the number of hidden layers. However, this didn't influence that much the training, and I think this is because the environment is not that big. I also have tried to change the parameter of the actor, still didn't get better results. So the next parameter that I have changed the key epochs to 10. And as you can see, we got better results. And this is because now the network learned more rare survival patterns more effectively from the noise gameplay data, while the PPO clipping mechanism prevents the major overfitting and keeps the policy stable. And here is a demonstration where the model have five moving obstacles, five dogs and five birds, and it's successfully stable and delivered the package to the location. And this also influenced as we increase the number of the birds and dogs, we are now able to get a better result for increasing these numbers. Also, another experiment that we have done is to experiment with the different rewards function. We have basically seen that if we have a better reward function, we get a better results because it gives the feedback guide for the agents onto how to fully deliver a better path for this package. So the reward function design is really important for the successful of training and learning. However, for the multi-agents, it was not that good. We have started using the multi-agent BPO for two agents and for two boxes with no moving obstacles. And as you can see, the results are really bad, and the model didn't stable and didn't learn. And as you can see, it's the demonstration. And due to the lack of the time, I have bending this for future work. So answering for our research question, we have successfully seen which algorithm perform better for this environment, and we have seen that changing the parameter really improve the performance. And also, we have seen that how challenging is the moving obstacles. We also see that the reward function is really important for how the agents is behaving. However, the multi-agents still needs a lot of work and research, and due lack of time, I didn't finish it on time. So this requires more research and exploring, like for each one of these experiments that I have done. It took approximately an hour to 30 minutes. So it was a lot of work. This is the whole project. It took me like 2 weeks. So at the end, we have learned all these important aspects, and this gives really good insights for future